Good morning and welcome to National Robotics Week kickoff event at the Smithsonian National Air and Space Museum. My name is Mike Holzlander and I'm the manager of on-site learning here at the museum. How many robot fans do we have in the audience? That's pretty good. Are you all part of a team that's here today demonstrating though? Any general visitors that like robots? Awesome, okay. Well, I think you're going to be in luck today. Today's program is going to focus on robotics education here in this country. We're also going to get a chance to listen to some of the premier robotics research teams from across the country as well. But before I introduce our first speaker, I'd like to take a moment to just say how important robotics and STEM education, which includes robotics, is to the Smithsonian. At the National Air and Space Museum, we are committed to educating and inspiring the nation about relevant STEM concepts like robotics. And we do this through preserving and displaying flight-related artifacts and information of historic importance and significance, developing educational materials and conducting programs just like this to increase the public's understanding of and involvement in flight-related areas, and conducting and disseminating new research in the study of flight and its related technologies. This museum is keenly aware of the impact that robots have had and will increasingly have on flight and space exploration. Robots have often been used in flight-related situations because of the dangerous or repetitive nature of the work, or because of their reduced cost, or because they could simply do the job better or faster than humans could. You can see many examples of these robots on display throughout the National Air and Space Museum. In fact, there are two in this gallery behind you. I'm not sure if you got a chance to see those. The DARPA DARPA arm robot named Robbie, and Robonaut 1, whose brother or cousin, I'm not sure of the relationship, is currently on the International Space Station. Robots are an important part of the stories this museum tells about flight, and I encourage you to explore the museum after this program to learn more about these stories and the roles that robots play. Now, let me introduce our featured speaker. His name is Anthony Mr. Roboto. Is that, did you give yourself that name, or? Okay, so it was given to him by his students. Mr. Roboto Nunez. He's the CEO of Infamous Robotics. He played a key role in bringing all of these robotics teams to the museum here, and he is a passionate and advocate for robotics education. So let's give Mr. Roboto a warm hand up on stage.
Thanks, Mike, for the kind introduction. So I'm here to talk to you about the state of robotics here in the U.S. Before I get started on my presentation, I just wanted to make a quick note on National Robotics Week. So the whole purpose of National Robotics Week is to really draw attention to the importance of robotics as an industry here in the U.S., but also to the next generation of our workforce in robotics education. And that's how we have to develop them. We have to develop this industry from the ground up here in this country, and the way we're going to do that is by educating our children now and preparing them for these future jobs. So, the state of robotics here in the U.S. Next slide, please. We've seen over the past couple years the rise of robotics mentioned in our everyday lives. One of the biggest seeing of that is in movies. We see the movie Chappie coming out later this year, a movie about an autonomous robot from the future, and then we see movies such as Robot and Frank there in the lower picture, and also movies for kids such as Big Hero 6. All of these movies are targeted to different types of audiences, but we're seeing more mention of it in mainstream society. Next slide. We're also seeing that universities are recognizing this trend and forming more specific robotics programs that specialize in even parts of robotics. And the two pictures I actually have up here are from UC Berkeley. And UC Berkeley actually dedicated an entire department to solely imitating the way bugs and little animals move. That's just one aspect of robotics. And as I'm going to show you later in my slides, there are many aspects of robotics. Next slide. So I'm going to start off this presentation by talking about ground robotic advancements that have been made, and to give you an idea of where we are today and where we'll be going in the coming years. I'll start off with ground robotics. So in ground robotics, there's different types of ground robotics. In assistive robotics, we have two different types of robots up here on the stage. The first one is actually one developed by INF Robotics, and that is a robot called Rudy. And the idea there is to allow seniors to age in place. We have a rising senior population, and we don't know how we're going to take care of them. We have developed a robot to actually take care of that for us. In the other picture, we actually see a good friend of mine, Dr. Rory Cooper from the University of Pittsburgh, and he's developed technology to assist individuals with disabilities. And on that robot, there's actually an arm, which most robot people refer to as a manipulator, and it's allowing them to be able to grab and move objects around. Next slide, please. So some of the interesting ones that we've seen on the news the last couple months, the first one on the left is actually a robot by Boston Dynamics. You may have heard a little while back, Google went out and bought up 8 different robot companies. The company that developed the robot on the left called Big Dog was actually one of those companies bought out by Google. Big Dog is actually a robot. It's kind of like a mule designed to carry about 350 pounds. The videos for this robot are very interesting. They have actually had to go up and down mountains, over holes, walk on ice. They've actually kicked it from the side, and the robot's able to recover and get up. The robot next to it is actually the Atlas robot. It is a humanoid robot that is designed for disaster relief, and this is under DARPA. DARPA's putting out a big contest to try to really spur humanoid development in the U.S. Next slide. Then there's also self-driving cars. Some of us have these cars that can assist us with parking, parallel parking. But a lot of that began back in 2005, 2006. On the picture on the left, you can see actually Dexter, which is a robot by Team ENSCO that developed part of the DARPA Grand Challenge. And that was back in 2006 in the desert. Nowadays, we hear about Google and other people bringing out robot cars. And the one on the right is actually a car by Mercedes-Benz that will be out in a couple years. And if you look closely at the image, you can actually see the driver's seat turns around. So they're intending you not to actually drive the car, so it will be fully autonomous. Next slide. Now let's talk about aerial robotics. There's 2 different types of aerial robotics advancements that have been very exciting. The first one is the traditional flight with quadcopters. These are ones with 4 propellers on the side. We also have ones with 6 that are called hexacopters. And then we also have this new one out of Brown University where they're imitating the flight of a bat. So it's winged flight. Very exciting to see. Next slide. In underwater robotics, there's been some very exciting advancements. MIT has developed a robotic fish that can actually swim underwater. Now, the difference between the robotic fish of MIT and fish from other universities and other companies is for robotic fish, they usually have joints. Okay, and the more joints you add to your robot, the smoother that motion becomes like a fish. Okay, in the MIT robot, they've actually found a way to eliminate those joints. So that actually makes it able to maneuver through the water faster, avoid obstacles. Also, they can use that skin for a sense of touch. The robot on the right is a jellyfish robot. Very exciting, developed by University of Texas. And that robot is actually hydrogen powered. So they don't have to plug it into a battery. They don't have to recharge it. They can kind of throw it in the ocean, and it can actually regenerate power that way. So you can see where things are going in terms of being able to let them loose, go in the environment, get information, and then months or years from now, we can extract information from them. Next slide. So since we are in the Air and Space Museum, previous slide, please. Since we are in the Air and Space Museum, I did want to, of course, talk about space robotics. The robot on the left is actually a robot by Carnegie Mellon University, and it's part of a competition that's being hosted by Google again, and it's called the X Prize competition. And what they're actually offering is a $30 million prize. 30 million, yes. For the first team that will land on the moon, travel 500 meters, and send some photos and videos back to Earth. So kids, if it's not cool enough to build a robot, it can also make you money. So the robot on the right is the Robonaut. We have it here in a museum. The interesting part about the Robonaut is that it can assist with in-flight repairs outside or inside of the space station. Next slide. So I want to mention quickly about some of the teams that you're going to see today. You're going to see all different types. You're going to see humanoid robotics. You're going to see assistive robotics, disaster relief robotics, flying robots, underwater robots. Next slide. And all of this is going to be on the floor, and including the now famous Robotics Inventors Club, a group of elementary school children who are really pushing the boundary of robotic invention. Next slide. So that is my presentation. Thank you for staying. It is my pleasure to be able to introduce the first team. The first team is a collaboration of the University of Maryland and the Naval Research Laboratory. And they are going to come up and present to you about their quadruped robot, which demonstrates locomotion and mobility in rough terrain.
Thanks for the warm introduction. As you heard, my name is Michael Coleman. I am a PhD student in the Department of Mechanical Engineering at the University of Maryland. Can you hear me louder? Better? Can you guys hear me now? Okay. As you heard, this is a joint collaboration between the University of Maryland and the Naval Research Laboratory in Washington, D.C. And today I'm going to be talking about how we can use what's called a central pattern generator to generate gates for the SimLab Allegro dog, which is down there on the main floor. Next slide, please. So I think the first question to ask is, why legged locomotion in the first place? Legged robots have great potential for navigating different types of terrain that, say, a ground-based vehicle or an aerial vehicle cannot. So I think a good example is if you look at the doll sheep that you can see in Denali National Park, they can scamper up these mountains that are incredibly steep. A wheeled vehicle could not do something like that. And if you had an aerial vehicle, you could not either fly close to the mountain because you might crash, or you may be able to fly for a very long duration. So really that's why you would want a legged robot to be able to scamper up the side of some mountain. And really the main focus of this research is we want to investigate the different challenges associated with moving a robotic dog in any direction. Next slide. So I've talked about this central pattern generator. And what this is a neural circuit that you find in lots of different animals in their spinal column. Mammals have a central pattern generator. Reptiles and fish and even the lamprey have these neural circuits. And what they are supposed to do is they enable locomotion by synchronizing joint oscillations. So if you look up in the one picture, I have a salamander. So there's different joints in like the body and the limbs. You want to be able to coordinate that locomotion so that you don't fall over if you're navigating terrain. And really the important concept is you can use a CPG to incorporate sensory feedback. So as an example, in the inner ear, we have a sense of balance. So if you start to fall over, you want to be able to compensate, catch your fall so you don't fall down. And you can use a CPG to do something like that. Next slide. So there's really two main CPGs for robots. Either you can control the joints of the robot or you can control like the positions of the feet. Most of them out there are joint-based. So one part of the CPG is going to drive, say, the elbow. Another part is going to drive the knee. And you want these to synchronize properly so that you can walk coherently. However, the work that we're working on is we use what's called a task-based CPG, where you're actually defining the positions of the feet. So one part's going to say how high is the foot going to lift up. Another part's going to say how far the foot's going to swing over. And really the key concept here is when you use this task-based approach of positioning the feet, you can avoid foot slip. The problem with foot slip is if you try to move your feet, you might kind of violate your ground contact constraints and you might end up falling over. So we can avoid that much better. Next slide. Really, there are several basic maneuvers that I think you would all be familiar with when you're using legged locomotion. And really what we want to do is we want to take these basic maneuvers and combine them together to make more complex maneuvers. So for example, you're going to want to start and stop when you're walking. You also are going to walk forward or reverse. Something else you want to do is you want to be able to turn in place. So that's like if I'm not moving the center of my body, but I want to change my orientation. I want to be able to do that. And finally, what a legged robot can do that's, say, a wheeled vehicle can is you can actually step sideways. Next slide, please. So I'm going to show some videos of these basic maneuvers. So can we get the first video going? So I think we're having some difficulties with the video here. Anyhow, we have the demonstration of the actual dog walking, which I think is more interesting. Really the important point here is the turn in place, the center of mass is stationary. Can we go ahead and go to the next slide? Yeah, we can skip these videos. Just go to the next slide. So there are some more complex maneuvers that you can do. If you're more familiar with like driving a car down the highway, you might be driving 65 miles an hour down the road, and you're also turning at the same time. And really, we can reproduce something like that by moving both forward and turning in place at the same time. So we can combine those maneuvers together. Another option you can do is you can also move forward while also stepping sideways. So that's like if you wanted to maintain your heading and like navigate around some obstacle, you can also do that. So, next slide. Yeah, so we'll go ahead and, my assistant Daniel has been walking a Lego dog for some time. Yeah, so the robot's having a little trouble with the carpet in this area. Where we do the research, we have linoleum floors, and that actually changes the way the feet lift off the ground. So it's a little hard to do the side step maneuver in this case. So as you can see, Daniel's just walking the robot using different controls. He has an Xbox controller that he's using to drive the robot. And literally what we're doing is we're assigning these different simple motion commands to the different joystick axes. So one is for forward, one's for reverse. You can sidestep sideways. You can turn in place as well. And he can do any combination of the three. Next slide. So as I said before, this work was in part performed at the Naval Research Laboratory. So I'd like to extend special thanks to the Merlin team, who's really been behind this and developing this platform. So we also have a booth out in the Space Gallery, so if you guys would like to drive the robot yourself, you're more than welcome to come by at a later time. Thank you for your attention.
Excellent presentation and a very exciting robot. The next team that I'm going to bring up is going to be from the University of Pittsburgh. They work under Dr. Cooper at the Human Engineering Research Laboratory, which is actually a Veterans Affairs funded laboratory. They've designed technology to assist individuals with disabilities.
Hello, everyone. We are from University of Pittsburgh. My name is Jorge Candiori, and my colleague is Joshua Chang. We're going to present, we're PhD students, and we're going to talk about our assistive robots. So I'm going to let Joshua talk about the robot first. So the next slide.
Hi, my name is Joshua Zhong, and we are from University of Pittsburgh. Here I'm talking about the project. We called it PERMA. It stands for Personal Mobility and Manipulation Appliance. Next slide, please. So the PERMA has been developed for, especially for power wheelchair user. As we know that currently in the United States, there are about 20 million people have difficulty using their hands and arms, including reaching, pulling stuff, dressing themselves, or even just pick up something on the floor. And it is estimated that on 2040, there will be like 20 to 30 million older adults that will have either moderate to really severe disability. So we are facing a large increasing population that will have difficulty using their hands and arms. So we started this project about 6 years ago, and it's the first robot that to increase the mobility and the manipulation for people with disability, especially wheelchair users. And it has originally designed with 2 robotic arms on the side, but here we only bring 1 robot here, and also it provides a novel track that can move the arm to the back of the chair, so to minimize the space. And next slides, please. So for this project, next slides. This project, we focus on the human-robotic interaction that increasing using all these provided sensors and interfaces to make the robot easier to use and much helpful for the wheelchair user, and to increase their independence and their quality of life. And so, and in the following video, I can show you, we will show you all this stuff. And the next slide shows that we work with closely with wheelchair users, with clinicians, and also we have VA hospitals and UPMC hospitals working with us, and we are test with wheelchair users and see how they respond to the interface and how they deal with this robot, and want to make this more much more helpful for them with their daily lives. And the following video, okay, next slides, and there will be a video shows that introduction of the PERMA. So PERMA provide really a lot of different user interface. It can be controlled by the remote user. It can be caregiver or family member not on the site, and you can control to help your grandparents like in the Florida. And also we have a autonomous function. It recognizes where the door handle is and figure out what's the way to open the door, and also figure out where to put the hands to pick up the solar can and bring that to the user. So we also test with a real world scenario, like in the machine shop using the PERMA robot. And we went out to the coffee shop and use the remote control to assist the user get a drink. And also we went to the staple grocery shopping and to test out how this can be involved in the wheelchair user's daily life. And that's our PERMA robot. Okay, Jorge will take over talking about the MeBot.
Okay, so next slide. What I want to say first is that in our lab, the mission of our lab is to improve the manipulation and the mobility on people with disabilities to improve their quality of life. So Joshua just talked about the manipulation, and I'll talk about the mobility side. And why we design MeBot, what is our motivation? So currently, every year, there are 100,000 wheelchair accidents in the United States alone. Some of the wheelchair accidents are due to tips and falls when driving outside of the house. And basically, there are two main reasons because of the tips and falls. Because of the environment where the wheelchair users usually drive in, and also because of the limitation in their device. Usually, some of the environments is probably the hills and slopes where they feel there's a lack of stability. They might feel like they're going to tip or fall. Driving in slippery terrains, like when you're driving a car where you can lose control and tend to drift. And the last one is also driving places with steps and curbs, where there's architectural barriers where the wheelchair are unable to, are limited to drive into. So in the next slide, our motivation is, next slide, our objective is to drive, to design MeBot. It's a mobility enhancement robotic wheelchair with the option to drive inside and also enhance the outdoor mobility. In compared to other power wheelchairs, it has the option to move the wheels, driving wheels, back and forth for better traction, and also elevate the wheels or lower down the wheels so you can access under the table, and also provide lateral pressure relief. But there are three main applications that I want to talk about. It's when driving outside the house. In the next slide, you're going to see the video. In the next slide. So next slide, you see the first application is called the level seat in uneven terrains. So you can keep the seats level, flat when driving in up, down the slopes, or in the lateral self-leveling by able to move the wheels up and down and compensate for the degree of the slope. In the video, you see that these are dynamic platforms that can simulate these type of terrains. In the next slide is the car climbing application. Just like it sounds, this is actually faster. The videos see, you can look like it's faster, but it takes around 2 minutes and a half. But the purpose of this is to be able to climb to a 8-inch step, just a regular ADA standards. So you can move, it's more like a crawling type motion where you can elevate the wheels and move the driving wheels back and forth so you can climb the step. And in the next slide, the last slide, is the slippery control or traction control. The purpose of this is to address the problem that the wheelchair can drift when driving in the slippery terrains like you see there. But when the control is activated, you can keep the speed and acceleration changes, so you can keep the wheelchair in a straight path, even in this type of slippery terrains. So that's our main motivation to develop these assisted devices. Thank you.
Okay, we're going to take a few questions. Any questions from the audience? If you have a question, please come up to the microphone. No questions? All right, I have a question then. So it's probably a different answer for all of you, but what really got you interested in robotics, and what kind of education, what kind of classes did you have to take to get into these types of research fields?
Well, I'm an electrical engineer, and I actually wanted to develop anything that can improve the people with disabilities. So I focus mainly on robotics, and any classes that I took is probably more programming or anything focused on electronics and design and development and rapid prototype as well.
So I guess I've always wanted to be an engineer for quite some time. And, oh, you guys can't hear me? I'm sorry. You have to stand really close to these mics here. So I was in my undergrad, and I was looking at courses, and I saw there was a robotics course, and I said, hey, that sounds interesting. I've always seen robots in movies, for example, and I'm like, maybe I could give this a shot. And after that, I got an internship with JPL, Jet Propulsion Labs, out in Pasadena. And since then, I've been hooked.
So my trajectory to the robotic is a little bit more complicated. So I got my mechanical engineering for my undergraduate, and also after that I worked for biomedical devices, a research center for 7 years, and then I moved to America to study to further working on the medical devices. But after that, since I was working on mechanical stuff, doing some mechanical designs, and also I taught myself for the electronics and the software. So Then I started my robotic project here at the University of Pittsburgh. So the courses I learned a lot. I think I like the mathematics most. I like to do the most calculations, and that really helps a lot with the robotics. Thanks.
So maybe you could also offer a bit of advice if there are any kids in the audience who are interested in getting into robotics. What subjects do you think they should concentrate on? Anyone?
I think if you really want to learn how to program robots, I think you should learn programming, right? That's a big part. So in schools, you'll get like a TI-83 calculator. You can program those. Everybody now seems to have a smartphone. You now have a supercomputer in your pocket. So you can learn to program your phone to do different things. There's also lots of different robotics kits out there you can buy. So there's the Arduino microcontroller, if you guys have heard of that. That's great for kids to play with, experiment with, have a good time. It is a bit of work to learn this kind of stuff, though. It takes, I've been doing robotic stuff for well over 5 years now. It's a lifetime commitment.
Okay, do we have any questions yet from the audience? Okay, I do have another question. I come prepared. So the video you showed with the self-leveling chair, this is out there. This question is out there. Could it potentially, if you had it on a boat, keep you from getting seasick?
Actually, well, if you think about it, you can actually put that in a boat. It will be like a second platform. So you see that the system is called the current system, the dynamic platform. That actually simulates also seasickness as well. But if you think about it, you can put a platform inside of the boat, so it can compensate for the waves, for all that type of motion, in order to keep the boat, that platform always level, regardless of what motion waves you have. So, yeah, but of course that's gonna increase the price of the boat. So. Yeah.
All right, thanks guys, appreciate it.
Okay, so we've seen some robots on the ground. It's time to get into robots that go into the air and underwater. Cornell Engineering will be showing off their autonomous vehicles, their unmanned aerial vehicle, and their underwater submarine, for which they finished first place in the AUVSI competition. The purpose of this submarine is to track down black boxes of airplanes. Some of that can be very relevant to what is going on in the news today.
Hello. I'm Brendan Quinn. I'm here representing Cornell University. I am on CUAir, which is one of our 24 interdisciplinary project teams, which represent 1,100 students. And here today with me is Alex from CUAUV, our autonomous underwater team, and Yogisha from CUAir, our autonomous aerial flight vehicle team. Next slide, please. So this is CUAir. Next slide, please. We are another interdisciplinary team of approximately 50 undergraduate students. We were formed in 2002 for the first annual AUVSI Student Unmanned Aerial Systems team. So what we do is we design and build a new aircraft every year for these competitions. I'll talk about the competitions in a bit, but we split our teams up into 5 sub-teams: our autopilot team, our business team, our electrical team, our mechanical team, and our software team. Next slide, please. So what we have to do for our competition is we have to achieve autonomous takeoff and landing. We have to get our plane to navigate waypoints and do a grid search of a very large field, capture images and do target recognition. We need to go and connect to a simulated remote intelligence center, and then we have to drop a relief canister based on what the competition asks us to do. That could be anywhere on the field, and we have to get that. Next slide, please. So these are our targets that we have to identify. So these are what we fly over. These are what we're looking for. And we have our camera on the bottom of the plane gimbal around and look at different points on the field to try to find these targets here. And so for our competition, we'll get points based on where the target is. If we can identify what shape the target is, the color of the background, and the color of the alphanumeric character, what the alphanumeric character is, and the orientation of the alphanumeric character, plus its location. Next slide, please. So this is our plane for this current year. This is EOS. This is the plane currently. It's still being built, but this is a CAD model of what the plane will eventually look like. Next slide, please. So in the past years, we have come second overall, first in mission, and so on down the list. Trying to go and build our plane to accomplish everything possible in a competition while trying to be as light as possible, efficient as possible, and to do everything that the competition asks and more. We're trying to revolutionize what we can do in the air. Thank you. Next slide, please.
Hi, as Brendan said, my name is Alex, and I'm on Cornell's Autonomous Underwater Vehicle team. So a little bit about our submarine. You may have heard of U.S. Nautilus-class submarines and German U-boats. Yeah, they're big, and they have nuclear reactors and diesel engines. But our submarine doesn't have any of those. We just use electric batteries. So it's an all-electric submarine, and we don't have any active ballast either. We use 8 thrusters strategically positioned around the vehicle to control our depth in the water. We have a depth sensor that tells us how far in the water we are, and then our computer reads that and tells us whether we need to go up or down to reach our desired target. Next slide, please. So a little bit about our team. Just like CU Air, we have four sub-teams: mechanical, electrical, business, and software. We have won 5 out of the past 6 competition years and 6 total wins in the AUVSI Robo Sub competition, which is held every year in a naval testing facility for acoustic pingers. It's a big underwater dome where it's basically an underwater obstacle course. We put our submarine in, and it has to traverse the obstacles, locate them, and perform various tasks, which I will talk about later. Next slide, please. Some of the challenges of building an underwater submarine are that, of course, it has to be completely waterproof. All of our electronics has to be in a sealed container that is completely sealed. And we also have to detect the environment around us using various sensors such as cameras, sonar, acoustic microphones, and we have to interact with this environment, such as pick up objects, listen to underwater pings, go to certain locations, and shoot through targets, for example. Next slide, please. So here are some of the tasks we have to do in the underwater. In the top right, you will see a 4x4, 2x2 grid of squares, and with holes in them, and we have to identify the correct color and shoot a torpedo through the right target. So if you see on our submarine, we have above our 2 cameras, we have 2 torpedoes, and those are fired using a burst of compressed air. So our computer centers on the correct target, identifies the color, and then tells the compressed air to fire a burst of air, and that shoots the torpedo through the water. In the bottom right, we have the driving tasks, which we have a little motor in the front of our vehicle that spins, and we position ourselves in front of the wheel, and we turn the wheel 360 degrees. After we turn the wheel, we have to shift gears. So we position ourselves in front of the red little shifter, and then we go up front of it and push down on it, and that's a completion of the task. And that simulates real-world tasks that you have to accomplish underwater or even in space, if you're doing a spacewalk, for example. A lot of these things can be applied to space missions where you have thrusters that control your position and orientation in space. So a lot of the math and research we do is applicable in space missions as well. Next slide, please. How do we do all this? We have a series of sensors. In the top left, we have our cameras. You may think it's easy. Oh, I see colors like a human. I can easily identify objects in the water. But what the computer has to do is it receives a string of numbers. And it's not even arranged in a square. There are no colors. You just get a sequence of numbers. And you have to program it to identify those numbers as first an image and then a particular color. And then you identify the shape of that object. And you have to say, OK, this is the correct object we have to fire through. In the bottom left is our computer, which is a kind of a shrunken down version of a desktop computer that we put inside our sealed hull. And in the top right is something called the Doppler velocity log, which tells us our velocity underwater. And that's very important because if we know our velocity, we can then use that to find our position in the pool. And if we know our position, we can accurately locate other targets in the pool. In the bottom right, an example of how our vision processing works. We start with the image in the top left, and then we pick a particular color that stands out, and we move on to the top right picture. And then we pick pixels in that image that are very bright, right? And we go to the bottom left image, where we get a nice, clean, square shape of our target. And then we find shapes between black and white in that image, and we identify the hole we want to fire through. And then our computer can center on that hole 10 to 20 times a second to find it, center on it, and fire our torpedoes. Next slide, please. Thank you, that's all we have.
Okay, so some excellent presentations so far, but we saved the best for last. It's my pleasure to bring up the next group. They are actually a group of my students. They are graduates of Infamous Robotics, Robotics Expansion Summer Camps, and they've gone through an 8-month process to build an entire robot, an intelligent robot, from nothing, from a piece of paper, sentence on that piece of paper, an idea, all the way through the prototype that they've designed here and tested it. So it's my pleasure to introduce the smartest group of children in this country, the most intelligent group of children in this country, and the future of robotics, building the Robotics Inventors Club.
Hi, my name is Kareem Jaber. I am 11 years old, and I am part of the Robotics Inventors Club, a group of children making a robot to solve a real-world problem and make the world a better place. Our club was created by Infamous Robotics, and we are sponsored by ENSCO and George Mason University School for Engineering. Next slide. To be allowed to attend this camp, you first must go through a series of summer camps that teach you the basics of building a robot, from building circuits to programming one. The Robotics Inventors Club has been working on a robot that we would like to share with you for 8 months since October, and we have transformed an idea to a whole prototype. The Robotics Inventors Club has 3 teams that work individually and together to solve problems along the way. The mechanical engineers, which design the structure of the robot, the electrical engineers, which design the circuitry of the robot, and the software engineers, which program the robot. Now, different team members will tell you more in depth about their team.
Hi, my name is Rayhan. I'm 11. The mechanicals are in charge of the structure of the robot and the beam which holds up the robot, and we were in charge of the dimensions too. We picked wheels for the robot, and the electricals were the ones to mount the wheels, and we were the ones to actually mount the other sensors.
Next slide. Next slide. So I am Lena, and I am 10 years old. I'm part of the electrical engineers. The electrical engineers, they make the circuits for the robot, and they draw the schematic and interconnect diagrams, which maps out where everything is going to be so nothing is colliding with each other, so it's all organized. We also put the circuits and stuff inside the robot, and we wired it all up so everything is connected with each other.
Next slide. I'm Addie P. Davis, and I'm 11. I'm part of the software engineers team, and we typed the program in C language, and it was 425 lines, and we made it go.
Next slide. The problem was that there was an Ebola outbreak in the U.S. at the time when we made Anna, so we made Anna. And Anna helps nurses, so nurses don't get infected while handling the patients. Anna delivers food, water, and medicine to the patients.
Next slide. Our solution to this problem is ANA, which stands for Autonomous Nurse Assistant. Autonomous means that the robot is not controlled by remote control, but controlled by commands and program. The drawing on the screen is one of the first drawings our mechanical engineers drew to design the structure of the robot. Along the way, many changes had to be made because of problems we ran into, such as the robot was too big to go through a doorway, or that the robot was too small to reach a bed. We did this from scratch without any toy kit. We completed it from an idea to a whole prototype. Since we did not have any kit, we ordered each individual piece, exactly which one we wanted, to make the robot the best it could be.
Next slide. Our solution was Anna. Our robot was designed, our prototype was designed to bring food, medicine, and water to the patient. If it was a contagious patient, the nurses wouldn't have to catch the disease because the robot would be able to do the work for them. This is made not to get rid of nurses' jobs, but to help them and doctors and other medical providers.
Next slide. This is not my slide.
Our robot's name is Anna, which stands for Autonomous Nurses Assistant. Autonomous means that it's without remote control.
Next slide. You guys should use our solution, well, anybody like hospitals and stuff should use our solution because it delivers water, drinks, food, and medicine without the nurses getting infected, which is good. And it's best used in hospitals and nursing homes. And
Next slide. So this is Anna in action. This is one of our tests. So Anna right now is going toward the patient to deliver the food and medicine on its 3 trays. Also, that person sitting on the bed is a dummy, so it's not going to grab his food. So right now, Anna is waiting for the patient to grab food. But since the dummy cannot grab food, Anna is now going back to its station. Keep in mind that this is only 1 bed, but we have programmed it fully to do 3 beds, then come back to its station.
next slide. In the future, to perfect our robot, we would like to make it waterproof so that if any drink spills, it will not mess up the robot, and so we will be able to disinfect it and wash it so it doesn't like infect anybody. And we would also like it to not serve just 3 beds, but maybe 5, 10, 15 beds. Who knows how many?
Next slide. After 8 months of work, we finally got our final product.
Okay, do we have any questions from the audience? Come on up, sir.
My name is Marwan Jaber. I'm from Chantilly. I just have a question for you guys. So when Anna actually arrives at the patient's bed, how long do you guys allow it to stay at the bed for the patient to actually remove the food, the drinks, or the medicine?
We had it wait for 6 seconds, but we can increase that or decrease that very, very easily.
And one more question. Do you guys foresee that in the near future that when you guys deliver also the foods to the patients, is it just going to be pills, or are you guys going to be actually possibly allowing it to perform like injectable medications in the future?
Well, we really don't know yet because if the patient can inject itself, yeah, but like the robot doesn't have arms, so it wouldn't be able to inject the patient.
Thank you.
My name's Joshua Harris. I come from Arlington, Virginia, and back to the underwater sub and the plane. Have you ever had any building designs of something that can go underwater and fly or float and fly, or have you just some designs for the future, or do you have nothing about it?
See, that's a very fun question. We haven't designed anything that'll both fly and go underwater, but we were actually talking about this yesterday when we were talking with the other team, because we work as separate teams, but since coming here, we started talking about what designs we could do that would make something both fly and go underwater. Good question, thanks.
Any other questions? Do we have any online questions? Nope. Okay, so maybe the Cornell folks, you can also talk about how you got interested in robotics and maybe what classes you think are important for kids nowadays to take to get into those types of fields?
Yeah, of course. So I've been interested in robotics and engineering in general since I was pretty young. I used to go and fly little kit planes and build stuff like that. So going into college was something that I always thought would be something cool to do, for a job, do for the rest of my life. So when I started picking what I wanted to do, I decided I wanted to do computer science, which will sort of give me the background to go and design anything or design the code to do any of the robotic stuff that I need to do to change the world. If you look around at anything in this room, it was built by an engineer. It was built by someone who had the know-how to do something amazing. So that's what you have to do, is you have to learn to do something amazing. So that's why I got into it.
Yeah, I recommend interested in math and science. Math is very fun. I always love math, and I always love science. And math and science come together, and you get robots, and it's a good way to get into the skills needed to build a robot. And if a lot of you are interested in computer programming, it's very easy to get into it at an early age. I started programming when I was in middle school, and it's really easy to pick it up. And I know a lot of you guys probably play video games and have PlayStation and games. You can also make your own games on the computer. There are plenty of ways to do that, even as a young kid, which is very useful, and I hope you learn how these robots are programmed and how everything works. So I think that's important.
I wasn't actually interested in robotics until I got to college. I was super into astronomy, but then everything, modern astronomy, just uses so much computing. So then I had to take a computer science class, and I was like, oh my god, this is so cool. And after I joined CUAir, my fate was sealed. So The other thing I want to say is I actually have a 6-year-old sister who I've been trying to get into computer science. So I teach her, like, Scratch is a really good program. And she's also goes to Girls Who Code, which does, like, really cool sessions on programming. So those are definitely things that you guys should look into.
Okay, and as a female, did you feel intimidated getting into robotics? I mean, it seems like it could be predominantly a male field, and so how did you feel trying to get into it?
I think most of the people in the CUAIR team were extremely friendly, so I didn't feel intimidated at all. But it's definitely hard work, so I feel like if there's anything that's intimidating, it's just like you just have to kind of do a lot of work and work hard at it, and you'll be fine.
But you would encourage other girls to get into robotics?
Definitely. It's a lot of fun. I think that's all I can say about it.
Okay. Any questions from the audience? Okay, this question is for the robotics club. Do you all plan to become engineers?
Definitely me.
There's one.
I want to be a surgeon.
And use robots?
Yeah, I want to go into robotics.
I want to do computer science and IT.
Okay. Great. And my last question, unless there's another audience question, was it just coincidence while you were designing Anna that the Ebola outbreak occurred?
Actually, we made the idea based off of the Ebola outbreak, so that's where the idea came from. It wasn't just a coincidence.
Okay, let's give them all a hand. Thank you, guys. Ladies and gentlemen, that's our program for this morning. I'd like to encourage you to come back at 1 p.m. where we will have several other university research teams presenting. In addition, if you're interested in asking any of these groups more questions, please visit them out at the Space Race Gallery located on the first floor right next door to this gallery. Thanks again, and enjoy the rest of your stay here at the National Air and Space Museum.